Okay, hi grade 12s. What we're going to work on in this little video is our molecular aggregates. So this is where we're looking at our molecules, and we can look at our molecule kits and build a whole bunch of different types of molecules, okay? And then remember, we're going to be looking at this group of molecular aggregates, and then we're going to talk about the physical and chemical properties that they have. These ones are much trickier than our ionic aggregates. We know that when we do our nomenclature, when we name our compounds, but they're much trickier because the first thing we'll need to do is to determine if these molecules are polar, nonpolar, or slightly polar. And of course, that has to do with a couple of things like the kinds of intramolecular bonds that are inside of the molecules, because then that will determine the overall polarity of the molecule, and then that's what we're going to use to help us figure out what kind of intermolecular bond this molecule will have with another one that's identical to it, so an aggregate of this. Or one we always talk about is, what if I have an aggregate of water? Okay, so how can we determine the polarity of this molecule? What does that mean to the strength of the intermolecular bond between the same kinds of molecule in an aggregate? And then how can we apply that to the physical and chemical properties that it has? Okay, most likely we're talking about our physical properties, because those are the ones that those are the bonds that break when you do things like change the melting point or boiling points. If you increase the temperature, the strength of the bond between these two molecules in one aggregate of water, that's what's going to determine how much energy you're going to need in order to break those bonds. And that translates into a melting point or a boiling point. Okay, so we're going to look at molecular aggregates. It can be a little tricky. We're going to be covering pages 27 to 31, and I'm going to use the solution set and explain using the solution set sort of as we go during this video, okay? Because there's a lot to kind of fill in. So either pause the video as we work through and fill in as I go, or you could certainly fill in parts of the lesson ahead of time and then watch the video and listen to me explain it, okay? You'll probably do maybe even a mixture of all those options as we learn. Okay, so remember, we've done our ionic aggregates. We've discussed that. Intramolecular bonds are called ionic. Intermolecular bonds are called ionic. They're easy. We did those first. Now we're going to look at our molecular aggregates, and the inside bonds that we can have are always going to be covalent. And then we talked about already the difference between the kinds of sharing you can get. Are those covalent bonds inside of a molecule, are they polar covalent or non-polar covalent? If they're between the same kind of atom, then there's no polarity to it. This is a non-polar covalent intramolecular bond. What if you've got something like water? This kind of a bond is between two nonmetals that are different, right? So there's polarity to it because one is more electronegative than the other. The electrons that are shared between these two atoms are going to be closer to the oxygen than the hydrogen. How do I know that? Because I know my periodic table trends, but I also could look up those values if you had to, okay? That is a polar covalent intramolecular bond, okay? Now, a new type of intramolecular bond that we're going to be looking at is a polar covalent bond, but what if the hydrogen is directly bonded to an atom that's either a nitrogen, an oxygen, or a fluorine? If that's the case, it makes this polar covalent intramolecular bond very polar covalent intramolecular, okay? Because there's such a big pull between those nitrogen, oxygen, and fluorines that it creates a huge polarity compared to some of the others. And that's what we're getting to in grade 12, right? We start talking about, yes, there's a generalization between this type of molecule, but guess what? There's a few more specifics, okay? So that's where we're headed. So of course we know that this is our big category, our molecular aggregates. They are made up of covalent molecules. How do we know that? Because there's a metal and a non-metal, usually different, but definitely can still be the same. And if you're thinking of which ones are the same, it's our diatomics. So feel free to, fill in as many examples as you'd like. If you're taking bio right now, then pop in some of our glucose molecules, or think of a few other big molecules that you want to name and practice naming. You can add them in. Okay, our intramolecular bond, remember our little short form we use for that? They are covalent, polar covalent, or non-polar covalent, just depends on the kind of atoms that you're looking at. And then for the ones that are covalent, of course, there are a few different possibilities. You've got a non-polar covalent molecule, no difference between them because the atoms would be the same. You can have a polar covalent, and then when you're looking at the overall molecule, you potentially could have a polar molecule as well, okay? And this is where we're going to get into the three different kinds that we're dealing with. Polar covalent and a very polar covalent molecule. So I'm going to show you a couple of differences between these. And there's a big note on page 31 that we're going to go into all three of those, because if you have a non-polar covalent intramolecular bond, it creates a molecule that is non-polar. Okay, there's no extra electrons that are creating a slightly negative character to any side of this molecule. Therefore, when it bonds with another of the same, because they're in an aggregate together, this is oxygen, one oxygen bonded to another molecule of oxygen, they have a very weak bond. Okay, this is the one that's going to be called instantaneous dipole bond. It sometimes has different names. So when you get to university and they start talking about these things called van der Waals forces, yes, we're talking about the same thing. We just have to decide which term we're going to use. We're going to call these instantaneous dipoles. I hope you remember this from grade 11. The next one are called dipole-dipole bonds. And you get this when you've got a molecule that has some polarity to it, because you've got a polar covalent intramolecular bond on one side here, the rest of them are between carbon and hydrogens, but let's say this is between carbon and chlorine. We'll use this as our chlorine molecule, or atom in this case. This molecule here has a slightly negative character over to this side, which means that when it's bonded to another molecule that has also a slightly positive and negative character to it, there's a slightly greater attraction because the molecules themselves have a little polarity to them. Okay? The kind of intermolecular bonds that this has between two molecules that are like this is called dipole-dipole. The last one, this is the one that's the easiest to remember because it's the one we talk about all the time, right? Why is water sticky? Why does water go from the roots of a plant all the way up to the leaves? How does the water get pulled up and the water sticks to each other, right? How does water move around in the human body? Water has a characteristic that creates these very strong bonds and very, very polar molecule, which means that when it's bonded to another molecule in that aggregate, water, 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 there's a very strong intermolecular force between these two. That's actually an interesting term there I just used. There's like controversy, right, in the chemistry world. Is this called a bond, this intermolecular bond between water and water? Well, people like to call it an intermolecular force because it's not a covalent or ionic bond. This is a covalent bond. The bond between these two is really an intermolecular force. It's called a hydrogen bond, and that's why it's a little tricky because we do use the term bond in each of these three examples, but really think about them as forces as opposed to a bond that is like a covalent bond or ionic bond. Those are actually bonds. Okay? Just remember that. Sort of tuck that in the back of your brain and just be thinking about that as you explain things as well. Okay, these are our three types. Can we go now to page 31? And I want to show you what that looks like in detail. Okay, so skip over to page 31 and I'm going to scroll through here and I'm going to find the answer sheet. And again, we're just going to go through the answers, and you're going to spend time on this as well, but I do want to explain some of this together. Okay, so we've got three types. Have you got them memorized yet? Instantaneous dipole, dipole-dipole, and hydrogen bonds. These are the only three kinds of intermolecular bonds we have for our covalent molecules in a molecular aggregate. That's a bit of a mouthful, isn't it? That's your title, and I want you to remember that, okay? That's what this is called, because when we did our ionic ones in yesterday's lesson, you were looking at intramolecular bonds called ionic and intermolecular bonds called ionic. They were the same and they were easy. Okay, these ones are different. And because of the intramolecular bond polarity can help us determine the overall molecule polarity, we're going to factor one more thing in the next day's lesson. We're going to look at how that affects the shape of the molecule, and then come back to this idea of polarity between the molecules that are in an aggregate. Okay, so we have to learn a little bit now, learn a little bit later, and then come back to it. We'll just sort of circle back to the idea of polarity once we learn all the different pieces that go into it. Okay, so you've already got a good understanding of polar covalent bonds versus a non-polar covalent intramolecular bond. We've talked a bit about the overall polarity of the molecule, and now we're going to look at what does that mean with regards to the intermolecular bonds between covalent molecules in an aggregate. Whew. Okay, here we go. So here are our three kinds. Okay, again, they're called forces, not really bonds, but we'll go with that. Three kinds. Remember, these are the bonds that are broken when you have a physical change. I am changing, I'm adding a little bit of heat to my water that's in a solid state, it's in an ice cube. What's happening? Great, some of those bonds are going to break. I'm going to heat it up even more. I've now got liquid water and I want it to turn into a gas. What's going to happen? All of those intermolecular bonds are broken. What kind of intermolecular bond? If it's water, I'm talking about a hydrogen bond. If it's just a polar molecule, I'm going to be talking about a dipole-dipole bond that break. And if I'm looking at non-polar molecules, what's happening when it changes state from a solid to a liquid or a liquid to a gas? It's breaking the instantaneous dipole intermolecular bonds. Okay, so here's the first one in detail with loads of examples. Instantaneous, let's get a different color here for a second. Okay, so here is our instantaneous dipole bonds. This is one of the three kinds. Again, somebody might call them a van der Waals force. Some people call them London dispersion forces, and they are all the same. Okay, you've got nonpolar covalent molecules. Give me some examples. All of the diatomics plus anything that is a hydrocarbon where you have just carbon, hydrogen, 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 hydrogen. This is, what's this one called? This is methane, okay? This is a nonpolar molecule. The magnitude of these bonds, intramolecular bonds, are equal and opposite. They cancel each other out. There is no overall polarity to this molecule. This is a non-polar molecule, okay? Someday I can show you what that looks like if you add up all the vectors and cancel them out like you do in physics, okay? I can show you how to do that, but trust me, there's no excess side that has a slightly negative or positive character to it because they have the same strength, the same magnitude, because a bond strength between a hydrogen atom and a carbon atom is the same here, 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 and here because they are the same atoms that are sharing the electrons. Okay, it also works if you have a molecule like this, and I'm going to make sure I set it up so that I know that the regions are all as far apart as possible. Monkeys eat peeled bananas. This is called butane. So here's our hydrocarbon with 4 carbons, all hydrogens around it. This molecule is non-polar. Okay, that's hard, isn't it? It's hard to remember all of these factors. So think about those examples as you've got them down. Make some notes there. Okay, and how does it work? Hopefully you remember this. Do you remember this from grade 11? Okay, at any given instant, what if the electrons that are sharing the pair happen to overlap? Okay, and at the same instant, maybe the electrons are over here, which causes the electrons to go over here, and you get a very, very weak bond. Very weak. That's a slightly negative character on one side of my hydrogen molecule, a slightly positive character on the other side, and this creates a very slightly a slight dipole, which creates a very weak bond. Remember what we talked about with the strength of these intermolecular bonds from when we did our ionic ones? Remember, if you have a weak bond, it's going to be very easy to break that bond. So how does that translate to something like a melting point or a boiling point? Well, not very much energy will it take to break these ones. So the boiling point, melting points will be much lower when you're looking at an aggregate of non-polar covalent molecules, like, for example, hydrogen gas. Okay, does that make sense? So now we're taking our information and you're going to apply it to the physical properties on one of the other pages that are in this section. Okay, that's the first one. The next one, let's go over this one again. Number 2 is called a dipole-dipole bond. So here we have to find molecules that are polar covalent. How do they become polar covalent? Remember, there's a slightly negative character on one side and a slightly positive character on the other. For example, what if I'm looking at an aggregate of bromine and fluorine put together? Okay, non-metal, non-metal. What's the name of this bond here? Intramolecular bond is polar covalent, meaning that you're going to have one side of the molecule with a slightly negative character. The other side of the molecule will have a slightly positive character. It's going to want to stick, bond to another one, because again, we're talking about an aggregate of the same thing. And so it's going to have a slightly stronger bond between this kind of a molecule than our non-polar ones, the first example. What's it called? It's called a dipole-dipole bond. It's a little bit stronger than an instantaneous dipole. Okay, so again, we're looking at our characteristics of molecular compounds and just looking at the difference between them. Okay, here's another example. You've got, actually there's 2 more right here on this page, which are great. Okay, what do I have here? SH2. Again, polar molecule creates a polar bond that's a bond that's stronger. It's called a dipole-dipole bond. Okay, and then can you see you've got carbon monoxide there? Again, you've got a polar molecule. Why? Because you had polar covalent intramolecular bonds. There's an overall polarity of the molecule, slightly negative towards this side. Why? Because oxygen holds those shared pairs of electrons closer to it, creates a dipole there, which means that when you're looking at a whole container filled with just carbon monoxide, they have a little bit of a stronger bond, and the bonds between them are called dipole-dipole bonds. So if you're changing the you're changing the state, you're going to be looking at melting points or boiling points. Which bonds are breaking? It's dipole-dipole, intermolecular bonds. Okay, and the last one is the one that we talk about quite a bit again. It's our hydrogen bonding. And so let me get rid of a little bit that's on here. But this is where you're looking at aggregates that are made up of very polar covalent molecules. Okay, and here's what you're looking for. You are looking for a direct bond between a hydrogen, a hydrogen and an oxygen, a nitrogen, or a fluorine, NOF. Okay, if that hydrogen is directly bonded to a nitrogen, oxygen, or fluorine, it makes this bond very, very polar, which makes the intermolecular bond between it and another one of its kind a hydrogen bond. Water is our example. There it is. Hydrogen is directly bonded to a nitrogen, an oxygen, or a fluorine, which makes this a very polar covalent intramolecular bond, makes my molecule a very polar covalent molecule, which means that the intramolecular forces between these in an aggregate of water, for example, is going to be a hydrogen bond. Okay, so that's what you're looking for. You're looking for a diagram where you can then put in the bond polarity, the overall molecule polarity, and then we use that information to tell us the kind of intermolecular bond we're dealing with. Okay, relative strength, well, have a look, right? What are the weakest? Instantaneous dipole. Then it becomes the dipole-dipole. And then we have hydrogen bonding. You've got some numbers down there to think about that. They are all weaker than something like an ionic bond. So we can say a hydrogen bond is strong, but it's not nearly the same as an ionic bond, right? If you're comparing, you're comparing two different things, right? So you've got to remember that. So we talk about it in terms of strong hydrogen bonds, but that's just within the molecular compounds, okay? That doesn't talk about not dealing with the ionic ones. They're in a league all on their own, okay? All right. Then I'm going to get you to go back and I want you to work through pages. Let me just show you which ones they are. The physical properties on page number 27 and 28. And then I'm going to talk a bit about the examples that are on page 29. Okay, good luck with this. It's a little bit of a tricky topic, but remember there are only 3 kinds of intermolecular bonds and I want you to memorize those 3. Good luck.